running. Streaming. Let's go. There we go. Okay, welcome back. We have project number 1. Hopefully we can wrap up any sort of leftover questions today and then turn in for tomorrow. Wednesday, there's no class, so take an hour to yourself, refresh, and then we can be back on Friday working on module 2. But that's the main logistics stuff. And then I guess the other part is that Carolyn and Peter had done a lot of work grading the first homework already, and Carolyn posted some nice suggestions on like either resubmitting work or submitting like next assignments, things to keep in mind. Okay. Anything? So on the working on the project, is anyone getting like errors or like issues, never-ending for loops, nothing's converging? How do I show convergence? Anything like that? No, everything's just swimmingly working exactly the way that you wanted. Yeah.
I was kind of confused with showing convergence with the time steps.
Okay, yeah. So showing convergence like with time steps, and we've looked at like convergence in 2 ways, right? Like one of them was actual like a log plot, like as time step decreases, then the error is decreasing on a log scale. Another one is just showing like graphically, like, hey, if I make time steps smaller, sooner or later, there's no difference in my solutions. So either way would work for those. Let's set up, because first we need an actual Euler integration, right? So I'll say T is going to be a lin space from 0 to 3 hours. Well, let's do like 4 hours just for fun. And we'll make 11 time steps. So dt is going to be t1 minus that t0, just some change in time, delta t. My t Euler is now going to be zeros for every point in time. My first value of Euler, I don't want to solve for the initial condition, I just want to plug in the initial condition. So that is my t0. Let me double check that. Yeah, t0. So I have like these constants defined up here. I'll copy and paste them down here. I'll start at 1 and go all the way to the last point in time, so that my t Euler of 1 will be t Euler of 0 minus k, I'll use like this backward difference, times dt times ti minus 1, I should say Euler, right? Minus ta. And I'm going to use like circles with lines connecting them, so I can keep track of like visually how many time steps I have. And I can see like some kind of exponential decay. But the question is like, is it going to converge to that exact, at least like if the question is, are my time steps small enough or are they too large? Usually too large is easy to see because something looks really wrong. So if I try to like just do it in 3 steps, that actually doesn't look bad. We need more time. Let's say 10 hours, 3 steps. All right, there we go. Now something looks like legitimately wrong if I try to take time steps of 5 hours. So 5 hours is too big. And that one is easy enough to see that it's not converging. So we'll go back to like 4 hours. And let's compare it to and I need that function, like the analytical function. So TA plus T0 minus TA e to the negative KT. TA plus T0 minus TA times np.exp of negative KB times T. I'll put this as like a black line. And with just 3 steps, like that black line is never gonna, it'll change like what it looks like depending on how many times I evaluate it. But this value of like at 2 hours, it's always gonna be that exact value, no matter what, because it's always the same function. It's like, well, how do I get multiple plots onto one thing? Well, if I can do it once, I can do it as many times as I want. I can take that whole couple of lines, highlight everything and hit tab, and now I'm starting to make like a for loop for n in 3, 5, 7, 11, 11, 21, 51. I'm just going. So now instead of saying like linspace is always 3, I'm gonna say linspace is n. And now I've got like 3, 5, 7, 11. Probably helps to keep track of these somehow. So as I'm plotting these, I'll make a label of like, let's say dt equals we'll say hours. And let's give this one a label too, right? The 6666666, that's I don't know, a little too evil. Friday the 13th was last week. So let's do like just 0.2f. 67. So now I've got like a pretty in-depth convergence plot where this black line is exactly what I think it should be, and all of these other colored lines keep getting closer and closer to that black line. And this is a nice like visual demonstration that as my time step decreases, there's no difference between like manually sitting down with pencil and paper and integrating this thing or telling the computer like, hey, just integrate this for me using Euler integration. So that's a nice like visual demonstration, convergence. Is that kind of what your question was? Is like, how do I show convergence, or was there a deeper question of like, what is the meaning of convergence when you say converge? Lost. It's too long of an answer. Any other questions on like either integrating or converging or solving, figuring out how to use, once we have something that is a model, how do we use that model to get an answer? No, everyone's nailing it. All right, let me check in, see what's really going on here. Do some investigative reporting. Make progress? Yes. Nothing broken yet? Errors? It's exactly what you expected? Well, some errors, but okay. I think we are working on it. Yeah. Cool. I mean, that looks like it's exactly the same as analytical. The only other step, so there you have like the opposite problem that I had. Like I was starting off, my time steps were too big, so I needed to show that as I get smaller, it's closer. Here you can back it off and say, as my time steps get bigger, I already chose the right time step. Yeah, it could be like some people like to have multiple plots, like a big title, like time step is something. Here's smaller time steps, it's good, bigger time steps, or you can put them all on one. Yeah. I do it on one, it's easier because I can do a full loop. Just put them all together. Yeah.
Okay. Thank you.
Oh, okay. Does it help to like rewind on the rewind play in slow motion? Yeah, because you kind of pull up, like you pull up this live stream of the current one, you could rewind and play in slow motion. No, the new channel. Right now, you could rewind and play it slow motion, and usually that helps some people. Yeah, yeah, and then it also, because it's YouTube, there are transcripts after the fact. Okay, so is that there? Because the internet is not changing, right? And it looks like at 45 minutes, I'm on around 80 minutes. So that's, I think that's happening with the, like, as you're changing the number of times, you're also, based on what I see here, it looks like you're changing your time scale and your steps. Usually what happens is didn't multiply the derivative by no, that one's fine. So in that actual just that because you're saying the change in temperature per line is delta total delta T. And now they're all oh, that top edge. That one we were talking about the difference between forward difference and backward difference. So like should that T minus TA 80 or 80. I put in Delta state. That's just a way of saying whether the first or second time. Yeah, exactly. So it came up a little bit. I don't know if everyone wanted to hear this conversation, but the question came up a couple of times of like, can we just plug in like negative times if we're trying to take our current model and understand what happened before 11 a.m.? It's like, yeah, we could definitely do that. No problem. I mean, no problems, but we just have to plug in the works, right? We have to think about it, how we want to do this stuff. So let's go back up. I know that if I have 50 steps, then I'm definitely converged. So I can use this Euler. I can use Euler or that analytical function, right? Like they're both, I've shown that both of them are equivalent ways of solving this problem. So let me grab like all my work that I did for that Euler integration. I'm going to say 51 steps. And I'm going to change this name to like T future and T past. I'll copy this one and then I'll use my fancy, if I can get my cursor back. If you hold control and click, oh no. Yeah, control and click, then you get multiple cursors and you can delete and type all at once. T future. Oh no. And then T past. And the difference between like taking steps into the future is that dt is positive, so it's a negative k times dt. But if I take steps into the past, then it's a negative dt. So this negative sign, I was subtracting that k times dt. Now I can add that k times dt, and it'll be the same thing as if I'm taking, for every time step, as if I'm walking backwards or walking forwards. Let's look at like red for the past, blue for the future. Oh, and then we want to say negative t for the past. I set up like a real world problem as an exact differential equation. There are a lot of temperatures that I calculated that are not physical. I mean, unless the cause of death was that the person was 180 degrees, but that's probably unlikely. I don't know. It depends on what was happening and how close to Bowser they were. So if there's some different things that I could do, like one, I could keep changing this time span, like I could kind of guess and check until 98.6 is my first temperature. Or like I already did the work, I could just take all those temperatures that are above 98.6 and set them equal to 98.6. So it'll be a flat line until something happened, and now it's kind of decreasing. So I'm gonna use Boolean indexing here, where I'm saying when t passed. So if I say t passed more than 98.6, it's taking every value of every temperature and comparing it next to 98.6. If it's more than that, it gives me a true. If it's less than, it gives me false. And then whenever I plug that into t passed, it's showing me all the values that are more than 98.6. Overwrite those with the value that I want them to be. And now look at this. I have a little more physical thing that 4 hours before 11, person was happy, healthy, maybe scared, I don't know. And then sometime 1 point something hours ago, something bad happened, and now there was a murder in the building. It's like, well, then how do I find that point? Like, I want that, right? Well, I already know that all these values aren't exact. Like, I'm the one who set them. So what I could do now is say t passed bracket, or wait, equal 98.6. And it's showing me like it was false for a long time and then true. Like, so those are all the points that were overwritten. And then look at the times where that happened. So it was true 4 hours ago, and kind of working my way backwards. The first time was like 1.2 hours ago. So 1.2, 60 times 0.2 is 12. So it's an hour and 12 minutes ago. So, not that. I want print time of death was 10. So 1 hour minus, so 10 a.m. minus 12 minutes is now going to be 9:48, right? 9:48 a.m. Now I've got of the different, and you'll, depending on what assumptions you used as you went through this, you'll get different values. Different's okay, but based on the work that I had, this is my like current estimate for time of death. That's one way of like, if you were trying to step backwards and then figure out, this is one way to do that.
Just before that, I think this will be weekend.
Yeah.
So I did that up to those different step sizes.
Yeah.
I just did like a small step size for one graph and a larger step size for this one.
Okay.
Is that fine? Or should I keep trying to put it all together?
I mean, it's up to you, because you do have kind of a side-by-side comparison. Yeah, if you wanted, you could say like, you could add a line that says PLT title, like say small steps not converged, or small steps converged, or steps not converged.
I put it in the title here, and then 81 steps.
Oh yeah.
9 steps.
Oh yeah. I would just put that in a title. Yeah.
Okay.
So that the output tells the story that you're trying to.
Okay.
Cool. Yeah, for all of this, like there's tons of different ways that you could go about this, and even like just the graphical convergence. That's one way. Another way is showing like on a log scale what is the rate of convergence as decreasing the log error is increasing. Yeah. The number, it's not the estimates. Financial. Down like that. Yeah, because when you're running into the past, I'm using the same value of time. Negative yeah, see 0 to 4, but 0 to negative 4. So you see where you have like that T and T mask, that shows all the times where you're still the calculated temperature. And the last value is 4 hours. Well, not very interesting. The first value is 1.6. So that would be right. 6 hours ago. Yeah. And there's other ways of like solving that problem. We can have that exact function. We plug in 98 pieces T. And that's the or you can use Python to solve that function. Oh, like what that is? So are you using the same kind of setup that I was? Yeah. Okay. So, oh, are you trying to write the function? Yeah, I'm trying to computer. At least in the way that I set up my code was, if that forward state just triples, then it uses in that function for the solve k, then t0 is on the right hand side, and then forward is false, then t1 is on the right hand side. Why do we all this there? In one case, if we're using a forward difference method, and the derivative is based on the current time. So the current time is 85 degrees. Right. And the derivative is based on the next temperature that it's just next one. If you're using backward, then it's reverse, where current time and current temperature is 80 and previous temperature. Yeah, so the left hand side is that
He's like, I think we're gonna get it. So I was like, okay. Well, I know like choice. Yeah. So is that? No, you said I don't know how that works. I was like nervous when he said order. I thought I was like hardware. I was not sure. They're nice for that. My best friends are actually kind of do use it, but also yeah. I looked it up too, and it's like on average.
so it's a function.
Yeah.
Undoing all that knowledge that we're going to be having back into. Yeah. Well, yeah, it's a simple curve. Every differential equation.
So I'm just gonna stay here and like watch a few videos and see my class. My class. Any thoughts?
And oh, we're like out of time, right? But
That's true.
what am I doing? K, B. So I just wanted to show some people were kind of using, and this approach works. Like if you like this approach and it makes sense to you, like all right, solve for past time and then overwrite those stuff with 98.6, end up with that 1.2 or whatever it happens to be. Like it'll be different for KB, KF, or if you take the average, and all those are different. But if you're like, it seems shouldn't there be a more accurate way of doing this, like something more repeatable? You can take like the actual function that we had and tell Python like, hey, solve this for me. Like I have a function. If I give you a time, you can tell me a temperature. Tell me when temperature is 98.6. So we're gonna say from scipy.optimize import fsolve, and then I'll say fsolve of TA, and TA has to be like a one input thing. That's why I'm saying that it's just a function of temperature. So for a given temperature, it'll give me for a given time, it'll give me a temperature. Then I have to tell it like some initial guess. So I'll say like -1. But I also want it to be like, when is it 98.6? So I want to take this whole thing and subtract 98.6 so that when this is 0, the temperature is 98.6. And now instead of 1.2, I get this like -1.16728.604, pretty close to what I just got, but now some extra sig figs. So fsolve is another. And fsolve is nice because no matter how complicated your function gets, even if it's not something that can be inverted, like this I could go through and do the math, find the log of 98.6 and solve for it, but the fsolve will solve any kind of nonlinear, numerical, weird problems for us. All right, thanks for the extra 2 minutes. And then I'll see you again on Friday. Take off Wednesday morning and be back on Friday.